Welcome to our Smart Energy videocast, where we touch on various interesting and relevant topics with aim at sharing insight and understanding of the matter. My name is Oddgeir Guðmundsson, and together with my colleague Jan-Erik Thorsen, we are here to introduce the smart side of the energy system and how the setup of the energy system can support decarbonizing the energy supply and fight against climate change. This session is followed by case-specific videocasts on how small and large-scale district heating systems play an integral part of sector coupling, which we encourage you to watch.
Let's start with what is climate change. Climate change refers to long-term shifts in temperatures and weather patterns. These shifts may be natural, such as through variations in the solar cycle. However, since the 1800s, human activities have been the main driver of climate change, primarily due to burning fossil fuels like coal, oil and gas. Burning the fossil fuels generates CO2 emissions, which is a long-lasting greenhouse gas. Greenhouse gases act like a blanket wrapped around the Earth, which disturbs the natural balance of incoming solar heat and heat losses from the Earth, essentially trapping the sun's heat and raising temperatures.
So, what are the alternatives to fossil fuels? First of all, the primary used fossil fuels are coal, oil and gas, and as energy vectors they are great. They have high energy content per volume, they can be found in vast quantities and are easy to transport. However, due to the climate change impact of their utilization, we need to move away from using them. And luckily there are many alternatives to fossil fuels. And the alternative is to use renewable energy. The renewable energy is covering heat or power derived from natural sources that replenish themselves, such as wind, solar, biomass, hydro and geothermal.
The question then becomes, how do we transition from fossil-based fuels to renewables? In theory, it is not so complicated to transition. The transition involves three major steps. Firstly, decrease energy consumption through energy efficiency measures. Try to use less. Second, cascade use of energy. If there is an unavoidable waste heat stream from the primary energy use, it should be captured and used for other purposes and thereby replacing primary energy. And third, change the fuel supply towards renewable energy sources, like as mentioned, wind, solar, biomass, hydro, or geothermal.
Now it's important to keep in mind that although the transition process is clear, there are specific challenges with relying on renewables. The main challenge with renewables is that they are often intermittent, and as such they cannot be guaranteed at the time of demand. We may have high wind at one period and then almost no wind at other periods. The sun is shining during the day, but then it's not shining during the night. Or there has been a lack of rain for filling hydro dams. And how can we address these challenges? Well, there are a number of ways that can be used to address them, such as invest in load shifting potentials to be able to move the demand in time and aligning it with the availability of the renewable supply. An example of this could be load shift of heating in building, as is shown here. Or we change our consumption patterns. For example, load our dishwasher or washing machine when there is a lot of renewables in the system. We can also invest in energy storages, and in that way we build up the energy system in a smart way, and commonly referred to as the sector coupling. Jan-Erik, will you tell me something about sector coupling?
Yes. And how does sector coupling help in the energy transition from fossil-based to renewable-based energy system? In simple terms, sector coupling is about connecting the different energy sectors together to realize a renewable-based and energy-efficient energy system in a cost-optimal way. There are some key elements included in sector coupling, and those are the energy networks, the energy supply, as we heard, energy storage, but also energy end use. By creating the energy system such that all elements can interact with each others, as indicated on this scheme here, it is possible to both minimize the instantaneous energy input requirements and to take advantage of and even extend attributes of one sector to the others. In popular terms, we can say that by exploiting synergies between the sectors, we get results that are greater than the sum of each individual sector.
Now, as we are coming from the district energy side of the energy system, we would like to discuss the role of thermal networks in sector coupling and what makes thermal networks especially relevant for sector coupling. Thermal networks have the unique ability of transporting low-quality energy for fulfilling low-quality energy demands, which are mainly heating and cooling demands from buildings or thermal demands of low-temperature processes. And this makes them uniquely qualified to exploit synergies with the different sectors. The three key abilities that make thermal networks unique for sector coupling. Then first, they enable cascaded use of energy, for example, by taking advantage of waste heat from power generation, waste heat from industry, such as production processes and data centers, as well as waste heat from manufacturing of synthetic fuels, which we will see more and more of in the future. Secondly, they also offer a great deal of energy storage potential, which originates from the low-quality energy they use. This comes through cost and energy-efficient thermal energy storage, which can be used for storing vast amount of energy for short, medium, and long term, even between the seasons. Third, they offer unique flexibility to the other energy sectors, as they operate with low-quality heat. They are effectively energy source independent, meaning they can switch very fast from one energy source to the another. This further enables thermal systems to offer balancing services to the power sector. And this can either be in form of dynamic grid balancing, or in case of excess renewable power generation, the system can capture that excess power for direct utilization, or alternatively, store the excess energy for later times by using the thermal energy storages.
So, what benefits do district energy networks reap from sector coupling? The key benefits, which has been mentioned earlier, is the possibility to use local waste heat sources, as well as the possibility to utilize renewable power at periods of low cost and when it does not put strain on the power system. This can significantly increase the cost competitiveness of the district energy systems. But there are also some wider benefits that district energy can achieve with sector coupling. Here are some examples. Exceptionally high supply security. Because in a coupled energy system, the district energy system will have access to a wide range of thermal sources. It's redundancy. Increased operational resilience, because in case of disruptions, whether that is due to global disruptions in single energy vectors, failure in one or more supply source or pipeline failures, the multiple, varied and distributed thermal sources will minimize the local impact.
Now, those were some general insights on what sector coupling is and the role district energy systems have in it. We thank you for watching and hope to have you on board again.